Hello and welcome to lesson 6.3, multiplying a vector by a scalar. So remember that anything like the absolute value of an item, like this, absolute value of k, is actually a scalar. So we're given a vector v and a scalar k, and a scalar vector is k units longer than v and has a magnitude of kv or kv. Now if k is greater than 0, then k is in the same direction as v, and if k is less than 0, then it's in the opposite direction of v. Now please also realize if k is actually a number less than 1, it's going to be smaller in size, which only makes sense. You're just multiplying that value by it. So here's an example. If you have the vector v, which we've got drawn right here, I'm going to take my ruler, I'm going to measure it. So I measure it at 1.3 centimeters. So what I'm going to do is I'm going to move my ruler over, and I'm going to draw something that's double that size. So 1.3 times 2 is 2.6. So this would be 2v. As you can see, it's headed in the same direction as the previous one, as v. And now I'm going to draw using my ruler again, same orientation, but now 1.2 times 3 is 3.6. And this would be the vector negative 3v. As you can see, headed in the opposite direction. So two vectors are said to be collinear if, when set tail to tail, the one vector is a scalar multiple of the other vector. So for instance, let me show you an example of two collinear vectors. So let's say this is one of our vectors, and let's say this is the other vector. So let's say this is A, and this is vector B. Well, what you can see right now is the vector B is some multiple of vector A. And those are collinear. So in other words, they have to be parallel to each other. If they're not parallel to each other, then it's not going to work. It's not going to be collinear. Okay, so some properties of vectors for scalar multiplication. First of all, there is a distributive property. So if you have any k value, that's a real number, and two vectors u and v, and you have k outside of u plus v, then you can just multiply k by u and k by v to get ku times kv. And, sorry, ku plus kv. Also, if there's any two scalars a and b that are real numbers, and any vector u, then it's the same as taking those two scalar multiples, working those values out, and then multiplying by the vector u as just taking one of the scalar multiples and multiplying by the vector u, then multiplying by a. And also there's the identity property, where there's the value 1, so 1 times the magnitude of u, 1 times the vector u, just gives you the overall vector u. Again, you don't have to memorize the names of these properties, but you just have to be able to apply these properties. Now, a linear combination of vectors is an addition of two vectors and two scalar multiples. So, in other words, something like some value times a vector u plus some value times a vector v. You could also have a subtraction between these two. You could use just a and b as the values of 1. These are many different options here. So let's take a look at how we can put all this information into practice. So vector AB, given the shape below, looks like two cubes put together. The vector AB is going to be the vector U. So what I'm going to do is I'm going to take a different color, something that's easier to see probably. Let's say green. So AB, this direction, is the vector U. AD, this way, is going to be the vector V. AE is going to be W. And AI is going to be 2W, so just double the size of that original W. So determine a linear combination equivalent to the following vectors in terms of U, V, and W. So you want to have vectors U, V, and W as your answers. So what we're going to do is we're going to go from point A, in this case, JA. So you're going to start with point J, and you want to get to point A. So to go from J to A, there's one possibility. I could go across this way, that vector, and I could come back down to A. Well, if I go a vector J to B, and I go from vector B to A, well, J to B is just the opposite of negative 2W. So it's the opposite of 2W. And the vector BA is just the vector negative U. So there we go. There's an equivalent vector. Linear combination. Okay, so we're going to do C to E. I'm going to erase the part that we just did. So now I'm going C to E. So just create a path that will get you from C to E. So one path is going from C to G, G to F, and F to E. If you want, you can write these C to G plus G to F, plus F to E. And then you just find equivalent vectors of each one. Well, the vector CG is parallel to vector W, so it's the same vector, W. G to F is the same vector as negative V, so minus V. And F to E is the same vector as negative U. So there's another equivalent linear combination. Okay, so let's try the last one. Last one, we're going from I to C. Well, I can go across to J, I can go all the way across to B, and then down to C. So IJ is equal to U. J to B is already negative 2W. And B to C is just the vector V. And there we go. There's your linear combinations. And thus concludes this lesson.